Okay. First of all thing for this for the course materials, the lectures that I shared on Avenue to Learn, it's you need to download the notes and then open the notes in your own computer with Office, the PowerPoint. You are not able to see the full information through the browser. There will be some issues about the Avenue to Learn to display the PowerPoint slides, and there'll be a lot of errors there for sure. So if you want to see the details, see what I show in the class, download the slides and go through the slides by yourself. I usually will post the slides one day before the lecture. Okay, so for the mathematical prerequisites, this one is very important. For most part of this class, we will need to use some calculus, some operations of the matrix, and apply a lot of the probability series and statistical knowledges. So I believe you all have taken some classes for your undergraduate program and master program, and those we probably have already learned. So I will not go through the details. I will just give you some hints about what kind of topics you need to review. Also, I have uploaded some materials, some reading materials on Avenue to Learn. Those PDF files or some, I guess they're also in a short textbook. You can go through the some introductions about those knowledges by yourself. For our first homework assignment, I also designed some questions related to the math, to the topics covered in this lecture, and you can try to work on those questions. And for some questions, you will be able to find out the potential or similar examples in the reading materials. Okay, with that, I will start with the introduction about the matrix algebra. This is an advanced operations for you to use for the trivial demand analysis. The first thing we will need to know is what is matrix algebra, and for the definition, it's just kind of the calculation based on the array of the values. So we will do the calculation for the set of the values simultaneously, and that's what we do for the matrix algebra. And actually, for the simulations for the transportation plannings, we mentioned that the data is very important. But in the softwares, in the database, most of the data set will be stored as in a matrix. Well, it could be two-dimensional matrix, it could be three-dimensional matrix, but those would be the type of the matrix. We will try to deal with this the whole data set as a matrix instead of the individual values, and that's the reason we want to use the matrix algebra. This kind of algebra will try to simplify the calculations, and also it will make your expression, especially expression about a lot of variables, simpler and easier for the others to follow. So with this one, we can get rid of a lot of notations. Like if you have 10 variables, you don't need to write them from A1 to A10. Instead, just write a matrix capital A. And for those variables, the matrix, it will have the similar meanings. Maybe just each cell will just represent one individual or one component from the set of the variable. And for now, let's go to see the detailed definition. For the matrix, we start with a single number, which we call it as scalar. It's the number that you're going to use 1, 2, 3, 10, 11, 20. So this would be in the scalar. It's called a scalar. It's just one single number. Definitely, that's not a matrix. But if you have a set of variables, say that you have an array of the variable with multiple values, and that one could be considered is defined as a vector. And here we will have the two examples. For the little a, it's a set of the vector with 5 values. That is 1, 2, 3, 4, 5. And we call this one as the row vector. And the second one, if you wrote the all these values in the vertical format, this would be in a column vector. So you have a single column. And this is the definition about the vector. Usually we're gonna use a small letter to represent the vector, and we're gonna use to differentiate the vector with respect to the scalar variables. We use the bold letters, so that if you see the bold letter, you know that it's a vector. If you see a regular one, then that will be the scalar. So that's the vector, and the matrix would be in a combination of multiple vectors. So here we can define a matrix. One example, capital A would be in the matrix with 6 variables: A11, A12, A13, A21, A22, and A23. So you can see that the format of this one is different from the vector. You actually will observe the matrix with the dimension of 2 rows and 3 columns. And this is actually the dimension of the matrix. Usually, if we write everything in the math format, we're going to use the bold capital letters to represent a matrix. And with this kind of bold or small or capital letters, you can then identify the scalar, the vector, and the matrix. Also, we know that for one matrix, you're going to have a dimension. And for this example, the dimension of A is 2 by 3, so we have 2 rows followed by 3 columns. If we have the same number, say that for the vector A with the same dimension, like n rows and n columns, then we define this vector as the square, this matrix as the square matrix. And so that's the brief definition about the matrix. And with respect to the operations of matrix, we have the transpose, the addition and subtraction, the multiplication, and the inversion. So I'll go through those 4 operations one by one. First, for transpose. The transpose is well, if you have the transpose for one matrix, it will generate a new matrix. And in the new matrix, you're gonna exchange the positions of the row and columns. And usually for the transpose of matrix, say that matrix A, we're going to use A prime or AT to represent the transpose. Either is fine, but usually we can use A prime to simplify it. So let's see how we're going to do the transpose. Assuming that we have the vector matrix A, and it has the dimension of 3 rows and definitely 2 columns. Then the transpose will change the number of the positions of each element in the rows and the columns. So with that, A11 will still be the same position, but for A21, it's originally located at the 2nd row and the 1st column, but you're going to change to the 1st row and 2nd column, and you can apply this kind of change for the other elements. So with that, the transpose will becomes a new matrix with the dimension of 2 by 3. So we have two rows and 3 columns. Let me see what happens about my. Just a moment. Let me do a little adjustment about the display mode. It looks quite weird. Just a moment. Okay, why it's not showing? Just a moment. I needed to. Okay. So I'm just. Let me just have a quick check. Are you able to see my slides, or it's a? It looks like there's some issue about my computer. Are you able to see my slides?
Yeah.
Yes.
Yeah, we can see it right now.
Oh, that's pretty weird. Let me just quickly close my PowerPoint, and I'm gonna open it again. I hope like I can use my pen to control it, but it doesn't work for now. So let me try to exit the sharing mode first. Okay, this one. Okay, hopefully it's working. Okay, guess it's working now. So we have introduced the transpose, how the transpose is working.
I'm sorry, we cannot see it, I guess.
You cannot see what?
The equation, the matrices.
Yeah. It's not here. It's just need to have the. You can see it now. Yeah, just need to display multiple steps. And so this is how you're going to get a transpose. Transpose is very straightforward, and it's easy for you to get it. If you are using Excel, you can just copy in the matrix and then paste it as the transpose. And with that, you will have the transpose of one matrix in Excel. But another thing, like if you have usually for the matrix, with dimension of, see that the dimension of m by n, the transpose will not be the same. Because for the transpose, the dimension will becomes m by m. If m and m are not the same, it will usually not be the same. But if we find that for some specific case, if we have a equal to a prime, then we can say that a is symmetric. Let me just give you one simple example. So say that a is 1, 2, 3, 2, 3, and 4, 5, 5, 6. And for this case, A transpose is also this matrix if you do the changes about the rows and columns. And in that sense, we say that A is in a symmetric matrix. And of course, if we want to get in the symmetric matrix, you have to make sure that the dimension m is the same to n. And also you need to check each elements in this matrix. So that's the definitions of the symmetric matrix. And the next operation we want to learn is the addition and subtraction of two matrices. So usually for the addition and subtraction, it's very straightforward. But for the matrix operation, we need to make sure that these two matrices, they will have the same order, which means that they have same dimensions. So say that if A and B, you want to do the addition of A and B, the A has a dimension of m by n, then B must also has a dimension of m by n. Otherwise, you cannot do the addition or the subtraction. So to do the addition and subtraction, you just simply add or subtract the corresponding elements. The elements in the matrix A, say that A11 should add to the element of the first one, B11, in the matrix B, and that's how you get the result. So here you're gonna have, let's see one general example. We have the matrix of the A with the dimension of 3 by 2, B is also 3 by 2, and for these two matrices, you're able to do the addition and subtraction, and now you get a new matrix, which is the matrix C. The dimension is also the same to A and B, as 3 by 2. And for the values, C11, C12, C21, C22, and so on, you can just quickly do the calculation by adding the values, the elements in the same position. So C11 equal to A11 plus B11, C12 equal to A12 plus B12. And the same process can be applied to the other elements. So this is also applied to the subtraction. If we have minus here, then C11 would be A11 minus B11, and C12 is A12 minus B12, and so on. So that's the operation of the addition and subtraction. And the next thing is the multiplication. It's a little bit complicated for the matrix operation. For the matrix operation, the multiplication can happen between the scalar number and the matrix. It can also happen between two matrices. I will go through them one by one. First, for the multiplication to the scalar number, say that we have the matrix A, capital A, with the dimension of 2 by 2, and you want to multiply A with the scalar number k, little k, then you just simply multiply k to all the elements in the matrix. So for k times A, you get a value as the first element is k times A11, second is k12, and the ka23 and ka22, and so on. This also applies to the other type of the matrix. And of course, there isn't any requirements about the dimension of the matrix. So that's about the multiplication of the scalar number. But if you are working on with the two matrices, say that for the matrix A and matrix B, then we must make sure that the dimensions of A and B matches with each other, which we call as the conformable rule. For if we want to do the production of A and B, we need to make sure that the dimension of the actually the number of the columns for the matrix A is the same to the number of the rows for the matrix B. So in this case, A has a dimension of m times n, B has the dimension of n times p. And by this production, you get the value, which would be the new matrix, that's C, with a dimension of m times p. So you actually canceled the value of n, and just use the for that one, you get the result from the get dimension from the number of the rows from A and number of the columns from B. So this is the condition for us to do the multiplication. And now let's see one example to see how we're going to do the multiplication. Here we have the matrix A. A has the dimension of 3 by 3, and B has a dimension of 3 by 2. Of course, here you can see that the number of the columns for A is 3, the number of the rows for B is also 3. So with that, you can get the matrix C with the dimension of 3 by 2, which will be determined by the number of the rows of A and number of the columns of B. And now we need to think about how to get the value of each element in the matrix C. So for C11, the calculation would be straightforward. So what you need to do, you first need to pick up the first column, first row of the matrix A, and multiplied by the first column of the matrix B, and multiply A11 and B11 plus A12 times B21 plus A13 times B31. So with that, you get the value of C11. And for the second value, C12, it's a similar thing. You still need to apply the first row, but instead at this time you need to time this one with the second column of the matrix B, and you can apply this equation to get the value of C12. And similarly, you can gradually move to the second row, third row to get the value of C21, C22, and C31, C32. So this is the way for you to complete the multiplication for two matrices. Well, that's my, just a moment. Okay, and here we have another example about how to do the a detailed actual example about how to do the multiplication. Assuming that this is the matrix A, it has the first row first column 1, 2, 3, second 4, 3, 6, last one 7, 8, 9, and you have another one for B, and then apply the equation that we mentioned in the previous slides. You can find out all the values about the elements in the matrix C. So C11 you get is 30, and C12 is 66, and you can get all the other values. So that's the multiplication. And another thing we want to further dig out is the properties about the multiplication operations for two matrices. The first thing we know that it's about the production of two matrices, and their orders really matters. Say that if we have two matrices A, B, so assuming that A and B can multiply with each other, but it's not necessary for us to know that A times B is the same to B times A. Here would be two specific examples, assuming that the dimension of A is 2 by 3 and the dimension of B is 3 by 2. With the rules of the multiplication, you get the matrix of C as 2 by 2. So that's the dimension. But if you reverse the order, you do the products of B and A. So we know that the dimension of B is 3 by 2, A is 2 by 3. We're going to cancel the two values, the columns of B and the rows of A. So eventually get the value as the new matrix D with the dimension of 3 by 3. Apparently, C and D are not the same. So we claim that AB is not necessarily the same to BA. So that's for the first property of the multiplication. And the second property is the chain of the multiplication. We have say that if we have 3 vectors, and we are able to apply the production of A times B times C. Usually we can, for the production of A, B, and C, you can do the production of B and C first, you can also do the production of A and B first. It doesn't matter. For the production of the three matrix, the result will be the same. So that's the chain rule. And the other things about the combinations of the multiplication and the transpose. If you have the if you find out the transpose of the multiplication for A and B, then it could be B transpose times A transpose. So here you need to change the order of B and A if you do the transpose. And these two will give you the same results. So that's the that's for the properties of the multiplication. And after that, I'm going to give you some introductions about some specific matrix. The first one is the diagonal matrix, where you will only have the values along the diagonal of the matrix, which the example is showing in this page. So you will only have a value of A11, A22, A33, A44. For all the other elements, there will be 0. And this is called the diagonal matrix. And there will be one specific diagonal matrix, which is called the identity matrix. And in the identity matrix, all the values along the diagonal would be 1. And the other values, the other elements will definitely be 0. That's the diagonal matrix. And there's a lot of benefit for us to introduce the identity matrix. For example, if you have the one matrix A, and A times I for the identity matrix, it will always be I. And with that, we can always introduce this redundant matrix, the identity matrix, and to do some expansion about the matrix, and then get our design features or properties of the equations or the matrix we defined. The third specific matrix that I'm going to introduce is called the Noun Matrix. The Noun Matrix is the one with all the elements be 0. So there's nothing there. Well, we can also say that this is a O. Well, of course, if we have the Noun Matrix, and for any other matrix A times O, it will also be null. You can try to check this calculation based on the rules of the multiplication. And basically, the null matrix will sometimes be applied for you to identify the whether there's meaningful values of the meaningful eigenvalues of the of one matrix. I will definitely introduce more details. The next feature about the matrix is the determinant, and this is actually one difficult part about the matrix, especially around matrix calculation. The determinant of the matrix is written as the absolute value of A, or we just simply write them as the determinant of A. The determinant exists only for the square matrix. So if the dimension of M and N are not the same, then we will not have any determinant. Only when M equal to N, we will have the determinant. And well, as I said, it's also very difficult to compute, especially for the high dimension matrix. But for the low dimension, like a 2x2 matrix, we can get the equation, simply get the equation. So we have the determinant of A as A11 times A22 minus A12 times A21. So basically find out the product of these two values minus the product of the another two values. So that's for the two-dimensional matrix. the 2x2 matrix. But if you have a 3x3 matrix, you still can do the computation by your hand, but it will take more time. So, well, I believe you have learned how to do this calculation in your previous class. I will not go through the details about it. You can either for this low dimensional matrix, you can do everything by your hand. But for definitely for the high dimensional, like the a 4x4 or even higher, rely on some computing softwares, MATLAB, Excel, to get the value. Do not do the computation by yourself. Do the computation by hand. So that's the determinant. We also have some properties for the determinant. It's very important features of the matrix, and we rely on the determinant for a lot of computations. The first property is like for the determinant of A and its transpose, they should be the same. There's no difference about their determinant values. And the second, if a row on the column of A is 0, if one row is 0 or one column is 0, then the determinant of A is definitely be 0. And another thing is like if every value, this is about the multiplication features. If every value in one row or one column is multiplied by k, then the determinant of A would be k times the determinant of A. So say that this I should say put this one as a new one, a new matrix. And so that's the multiplication features. And another thing, if the two rows or two columns, it's fine. They are interchangeable, the sign, but not the values. Then the value determinant of A will also changes. So this is another specific features of A. And if two rows or two columns are identical, they have the same values, then the determinant of A will be 0. Also, if two rows or columns are linear combination of each other, then A will also be 0. And another thing, the next feature is like if each element of the row or each element of the row or each element of the column multiplied the constant, and added to any other rows, then A will remain unchanged. So that's the we also have two additional features. For two matrix A times B, the determinant of A times B will be the same as determinant of A times determinant B. And for the diagonal matrix, the determinant will be relatively simple for you to compute. It's just the product of all the diagonal elements. Okay, so that's the features, the properties of determinant. And what I see in the message in the meeting chat, let me just go through the message. What the questions like for the exam, do we have to compute the determinant of the big matrix by hand? Definitely not. So you will probably ask to do the computation for 2-dimensional or 3-dimensional, but definitely not for anything higher than 4-dimensional. And if that's the case, you will be allowed to use the computing softwares to get the results. Okay. If there's no questions, I will jump to the next one.
Sorry.
Yes.
I just have a small question. of
Yeah.
the previous slide. So, so you said that A is distinct by B, which is a matrix, right? In
Yes. It's not a. I probably let me just move to the previous one. Okay.
sorry.
Guess you are talking about. You are talking about the third one, right?
Yes, exactly.
Yes. Probably the description of this one is not quite good. Let me just give you some examples, giving a quick examples.
Okay.
So say that this feature indicates that say that A equal to A11. I'm just using two-dimensional 2x2 matrix.
Yeah.
A2, A21, A22, and here B means that KA11, KA12, and A21 and A22. So this is kind of the assumption of this feature, and if in that sense, well, let me just change this one to B. The determinant of B will just be K times A.
Yeah. Now I see it. Okay, perfect. Thank you.
So that's how the this feature is described.
Yes, that makes sense. Thank you.
Okay. Any other concern? I may not I'm not putting the sign here the notation here correctly, but you can follow. You can use this one as the feature. Okay. Well, if no questions, I will jump to the next one about the definitions of the rank. The rank of the matrix is defined as the number of the linearly independent rows. How many rows are independent of each other? Or the linearly independent columns, this will be interchangeable with each other. And also we have some definitions about the independent vectors, independent rows or independent columns. Each row will be one vector, each column is also one vector. So the for the set of the vector, they say that they are linearly independent to each other. Then we must be able to find out in the scalars from say that C1, C2 to Cn. And if we do C1 times A1 plus C2 times A2 plus until you get a Cn times n, you must be able to find out in the non-zero set of the vector, the scalar values C1, C2 to Cn to make this equation valid if they are dependent to each other. If they are not dependent to each other, then we cannot. So that's the definitions for the rank. It totally depends on the number of the independent rows and columns. For the matrix A, if you know the dimension is n times p, and also we just assume that p is smaller than n, then the rank should be smaller than p. But if we find the rank is p, then we say that A is has the maximum possible rank, and it's called the full rank matrix. And of course, for the matrix A, the highest possible number of the rank would be the minimum value of n and p. So this is the feature of the rank. And the last piece of the matrix background is the inverse of the matrix, which will be, the definition will be very similar to the inverse of the scalar number, but also is only applied to the it only applies to square matrix. For the matrix, say that matrix A with a dimension of n by n, and if you find out in the matrix B, and make sure that you do the computation and you find that A times B is I, or you find that B times A is I is the identical matrix. Then we say that B is the inverse of A, or we say that A is the inverse of B. So that's the definition. And for any matrix which has the inverse, we say that it's a non-singular matrix. And for the matrix which does not have the inverse, then it will be defined as a singular matrix. So that's the inverse and the singular and non-singular matrix. If the matrix exists, we must see that the determinant of A is not zero. Only if when A is not zero, we can show that the inverse exists. And also we have some features. We also have some features about the operations for the inverse. For the inverse of A times B, the two matrix, it equals to B inverse times A inverse. You need to change the order. And for the transpose, the inverse of the transpose for A, so you can actually change the order of the inverse operation and the transpose operation. So that would be the transpose of the A inverse. And one last thing, the inverse of the inverse of one matrix. So A inverse A to the power minus 1 to the power minus 1 definitely will back to itself. So that's the feature of the matrix. With that, I finished all the definitions about matrix. And well, if you have any questions, do you have any questions about it? Of course, I skipped a lot of details about the some definitions, some operations, rules. Just assuming that you all know how to do it from your previous classes. Okay. Okay. If there's no questions, I will quickly go to the calculus. Calculus is another huge part that we have to prepare for this class. Well, there will be some. I'm gonna start from the definitions. For the calculus is kind of the mathematical. Calculus is kind of operations for the function, and the function is kind of the mathematical relationship between two variables. Say that the input variable x and output variable y. And generally, for each input variable, there's only one output. And with that, we're going to have the questions like, if we are providing the arbitrary line in the xy coordinates, and how many points you're going to intersect with one function? Were you able to get more than one intersections between the vertical line and the function that you propose? Do you think it's possible? So, well, the answer is it's usually impossible to get the more than one intersection point, unless you have some shape described by the equation, but it's not the function. So usually for the function, this could be the x, it could be y, and generally you only have one intersection with the vertical line. So that's what I mean here. For the function, we will have the discrete function. We have the continuous function. If the function has a small change in x, also has resulting in a small change in y, then we say that this is a continuous function. And the features, the question we're going to have is like, were you able to draw a continuous function without lifting your pen from the paper? And that the answer, because it's continuous, the answer is definitely yes. And we will not see any gap along the function, and there's no holes, no skips for any values of x. So this is the discrete function, this continuous function. And for the continuous function, usually we will have we'll be able to do the derivative for the function, and that's one key part of the calculus, and which we call the differentiable functions. The differential indicates that the point at which at the point of the function we are able to find out the derivative of the function. And also I'm going to show you more details about what's the derivative. For the continuously differentiable function, it means that the function can be is differentiable at any locations of x based on its definition, based on its specified range. And if the function is differentiable, then we say that the function is continuous. But on the other side, if the function is continuous, it not necessarily means that it's differentiable. So it could be something, some function like this. Then it's not at those critical points, they are not a differentiable. They are not a differentiable point. When the function is differentiable, we can then use the power of the calculus to get more features, get more properties. So for the calculus, one of the key components is the derivative of the function. The derivative of the function will represent the rate of the changes to the function. It means that if we have the changes in small changes in I at x direction, what's the rate of the changes at the y direction? So the if we draw everything on the in the coordinate, the derivative will usually represent the slope of the tangent line at the point. So one simple example is like if we have the second order function x and y, the derivative will just represent the slope of this line, this tangent line at the point. So this would be the derivative. Or we say that y prime x. And it measures the amount of the changes at y direction if we are provided with the small changes in x. But if we go to some specific example, for example, for the linear function, the derivative would usually be constant. Say that usually for the linear function, we read them as y equal to m times x plus b, and m and b are both the constant values. And the derivative of y at any point of the x will be the value of m, because we know that for the linear equation, definitely y and x. For the linear equation, at any point, if you try to draw the tangent line, it will be overlapped with the original line. And but for the nonlinear function, the derivative is not constant. It could be usually would be in the function of x, depending on how complex, how complicated the function is. For the operations of the differentiation, there will be a lot of rules. Actually, a lot of rules for the one variable functions. We can apply those would include the power rule, derivative of the constant, the chain rule, product rule, quotient rule, and addition rule. So again, I trust that all of you knows these rules from your previous class, so I'm not going through the details about it. For the function, you can actually apply the derivative once for the function. That would be the first order derivative. You can also apply multiple differentiation for one function. Apply it once, twice, three times, four times, or even more. with that you can get a higher derivative, and which we say that a higher order derivative. And for some functions like the higher order polynomial functions without any factorial or the exponential component, then eventually the higher order derivative will result in the value of 0. So say that the so fx equal to x to the power of 4 plus 2x cube plus 4x squared plus x plus 5, and the first order derivative will give you 4 cubic x plus 6x squared plus 8x plus 1. But you can also do the second order derivative, the third order derivative, and the first order derivative, and the fifth order derivative. Well, eventually get the find out the value will be 0. You can try this one by yourself to see how it works. But there are also some functions. Say that the typical one would be the exponential functions. You cannot do any derivative. No matter how many derivations you made, it will never be 0. And actually, for this case, if y equal to exponential x, y prime will still be y. It will still be exponential of x. And there are also some other functions, the log functions, the inverse functions. They all have some difficulty for you to get a higher order derivation and make them be 0. And as I just mentioned, that the exponential functions and log functions is really hard to do to deal with in the calculus. But in the trivial demand analysis, the log functions is very useful for us to simplify the some analytical analysis, the gravity models, the discrete choice models, and so on. So the we use the log functions a lot, and with that we will need to think about how we're gonna do the calculus with the log functions. And also the log functions can, well, it's in the math, log functions is very useful for us to understand the exponential growth and the decay. It's a opposite of the exponential functions. So here would be some definition. If y equal to the b to the power of x, then log by will be x. We will show you what's the power applied to b. And in practice, a lot of time we're going to use the Euler's number, which is a constant that is around 2.71. It's in the standard number that we're going to use for the exponential functions. And usually for the log x, it will represent to the log e of x. So that's one thing. And sometimes we also use the base of the log as 10. With that, you can simply find out what's the digit you applied. Say that 10,000, well, for the log of the 10,000, it's just to be 4, and represent x will represent 10 to the power of 4. Something like this one. I can give you some simplification. And for the numbers, for the values that you play with. So that's for the log function. And there are also some rules for us to use the log functions. The first thing for the log of ex, exponential x, definitely it will be x. And it can also be extended to the general function, the line of the exponential of gx will be in the general function of gx. Any functions applied to the power of the Euler number. And if we have the exponential of the line x, and of course it will be 1 bx. This is opposite, means that the log function is opposite to the exponential function. And of course it can be applied to the general functions. Exponential of the line hx would be hx. And for the product of two variables x and y, line of x times y will be the line of x plus line y. And similarly, if you want to find out the ratio of x and y, you're going to have line x minus line y. So that's all. Especially that's the beauty of the logarithms. It's able to change the product operations to the addition and the subtraction operations, and this will reduce the calculation complexity a lot. And the last thing is the log of the power. So the line of x to the power a will be constant a times the line of the x. So you also reduce the complexity for you to calculate the value of on the power products, the power operation. So that's the logarithm, the fundamental rules of the logarithm. And regarding to the derivations, if we have the logarithm function, say that it's a line x, the first order derivative will be inverse of x. So this is the rule we defined. And now the next thing we want to check is how we're going to calculate the first derivative of line 2x. So there will be multiple ways for you to do it. You can use in the chain rule. We know that the line 2x is actually equal to line 2 plus line x, and then take the derivative of the first and second component. For the first component, it's constant, so it's 0, and for the second component, line x is just 1 over x. So this is the derivative, derivative for the logarithm, and we can also go to see some general functions. Say that you want to do the first order derivative of the line gx. Then it's better for us to use the chain rule. With the chain rule, we can then find out the calculation of the result. The result as the derivative of g and the derivative of the line function. I'm going to show you the details later. So here's one specific case for the derivative of the exponential function. Usually for the exponential function, the first order derivative, whatever the higher order derivative, it will be the same to itself. And with that, we will need to check what's the first order derivative of exponential 2x. So to get this value, we need to get the chain rule. So assuming that gx equal to 2x, then you're going to have the function f gx will be the exponential of 2x. That will be the exponential of the gx. And with that, with the chain rule, the first order derivative will be df divided by dg, the first order derivative for the so that's the df dg, that is eg times dg over dx. Gx is 2x. So you can quickly get the result for the first one as eg. For the second one, that is 2. So you get the result as 2 times exponential of 2x. So that's the way for us to handle the derivative of the exponential function. And so for all the topics I mentioned previously, we are only dealing with one input variables, but in reality, especially for the travel demand analysis, we need to think about more than one variables. It could be 2, 3, or 4 variables. And in that sense, when we are introducing the calculus, we need to think about the partial derivative, which will be the derivative to one specific variable, and the total derivative, that will be the derivative to all the variables. Before we dig into that area, we want to learn the definitions of the multivariate relationship, which will show the output and the function of multiple variables. For example, like in the transpose system in travel demand analysis, the number of the trips could be in the function of the income, could be the function of the structure of the household, and so on. And for the demand of the energy efficiency of applicants, it's also like this is kind of the economic example. The market demand depends on the income of the residents in that area, and also the price you list for the for those applicants. And there are also some other examples for them. The growth of the populations depending on the natural reproduction rates, the rate of the growth of the predator populations, and so on. The partial derivative will help us to understand what's the small changes of one specific input variable, and what's the impact of this change to the output variable. And but you know that there are also some other variables in the function, and this will make the analysis complicated, and it means that the changes is also affected by the other variables. For the partial derivative, usually we're going to use the addition rule for the derivative to distinguish the each of the term. Like if the function has multiple terms, add them together and using addition or subtraction, then we need to find out derivative of each one of them, and do the differentiation for each term one by one, and this will help you to minimize the potential errors in the calculation. And if you are doing the differentiation with respect to the variable x, then only the term with the x will be considered. For the other terms that are not related to x, you can consider them as a constant. And in that sense, the derivative of those constant term to x will definitely be 0. So that's the fundamental rule for you to find out the differentiation with respect to x for the multivariable function. And also we will have we need to know the cross partial derivative, which means that you need to find out the derivative of multiple variables. For example, if we have the function of fx and y, there are two input variables, x and y. For the cross partial derivative, we will first do the first order derivative of x, and then do the derivative of y. You can also do the other way, first get y and then get x. So that's the cross partial derivative. And for the multivariate relationship, we also want to see what's the total derivative. The total derivative will represent the changes in the multivariate function with respect to all the variables. What if we have the changes for all variables? What's the total changes of the of this multivariate function. So to get that, we're going to sum the partial derivative for each variable and multiply it by the changes in that variable. So then we're going to have the total derivative for the multivariate equation. So that's the derivative part. For the calculus, another important operation we need to do is the integration. So for the integration, we're going to try to, well, it's basically designed to find out the areas under the curve on the line. So for example, if we have a simple question, and the basically the integration say that from 0 to x1, the integration for fx from 0 to x1 will just show what's the area behind the line and about the x-axis. So that's the integration. And usually the integration is in the reverse function of the differentiation. For example, if we have a function of fx, and then the integration of df dx will be fx, but you still need to get a constant value because you don't know what's the reference point for this function is. And this is this constant. If we do the derivation, for this component, x, the letter c, which is constant, can also be removed. And also, if you want to determine the value of c, you need to know the boundary conditions. What's the values of fx at x equals 0, or what's the value of fx at the value of x equal to x1. So that's the definitions of the integration. Usually in the study, in the math, the integration is very useful to get the when we want to find out what's the changes, what's the total changes for the output if we have the changes in some variables. And the for the derivative, they may have very for the integration, they may have very different formulas, but their derivative could be the same. Here is the here's the example. So if we have the fx equal to x squared plus 300, then the derivative could be 200 or 2 times x. If we have the function as x squared minus 500, you will still get the first order derivative as 2x. But apparently, these two are not the same. So if we do the integration for 2x backward, you will eventually get the result as x squared plus c, and you need to have the boundary conditions to identify what's the value of c. And this is the clear difference between, for us, that's also the major reason for us to introduce the constant term in the integration operation. Also, we have some rules, some similar rules about the integration: the power rule, exponential rule, logarithmic rule, the integral of the sum, the integral involving the multiplication, the substitution, and the integration with parts. Again, I'd say that I will not go through the detail. There will be too much contents in this area. You can go back to check your previous class or go through the reading materials I shared with you. One last thing I want to include in the calculus is about the optimization. How we're going to use the derivative and integration to find out the optimization points and identify the errors behind. So for the optimization, usually we'll rely on the first order derivative, and if the first order derivative is like dy over dx is higher than 0, indicates that the function is increasing, so the slope is positive. But if dy over dx is smaller than 0, which means that the slope is smaller than 0, means that the function is decreasing. But the tricky part is that at the point dy equal to dx, at the point dy equal to dx equal to 0, or dy divided by dx equal to 0, which would be the point with 0 slope, and that could be defined as the optimal point. But the things like you need to pay attention about the optimal point. It could be for this case, it could be the maximum, but for the other case, it can also be minimum. So it's this condition only tells you these critical points with maximum or minimum values without any increasing and decreasing around that point. And it's also possible to be some inflection point that will be related to some higher order functions. For example, for the 3rd order function, this could be x cubed. And at this point, I may not draw this one quite good. At this point, the value of the first order derivative is also 0, but it's neither the maximum nor the minimum. So in order to further identify whether this point is the maximum value or minimum value or the inflection point, we need to get the 2nd order derivative. So in the 1st order derivative, we can find out where the critical point it is. It could be minimum, maximum, or deflection point. Then we take the 2nd order derivative. So the d square y divided by dx square, the 2nd order derivative. And if it's if we get these two conditions, dy over dx is 0 and the 2nd order derivative is positive, then this is the minimum value. If it's this should be the case for the convex function. But if we have dy over dx equal to 0, but the 2nd order derivative is smaller than 0, it means that this will be the maximum value. And typical example would be one concave relationship. So this is the this is about the maximum and minimum value, how we're going to use the 1st and 2nd order derivative. And the other things like for the dy over dx, it's not necessary to be the minimum or the maximum values. It could be the but it could be the deflection point. For the deflection point, if the 2nd order derivative is positive, then we can make sure that the point is a minimum value. If it's smaller than 0, it's a maximum value. But only when the equal to 0, this would be in a special case, and we have to deal with that. Usually the inflection point is defined as the point where the function changes from the concave to convex or vice versa. So it's just the example as I showed for the 3rd order function. And if you find out dy over dx is 0 and 2nd order derivative is 0, then you can claim that it's an inflection point. But this is just a necessary point. It's a necessary condition. It's not the sufficient condition. at the inflection point, it just tell you how the trend of the flow, how the trend of the slope is changing over the time, but it does not give you the maximum value. It does not give you the maximum value or minimum value. It's just some turning point instead of the maximum minimum value. Okay. Okay. I guess I finished the most part about the calculus, and it's already 4:20. So I want to take a break for 10 minutes, and in the meanwhile, if you have any questions, you can ask, or you can keep the questions after the break. Okay. Again, as I said, that this is most about the review of the preliminary knowledge in the math. So you will probably can find out more details about these rules, the properties in the reading materials, or from your previous course materials. Okay, if you don't have any questions, I will probably turn off my camera and the mic, and we're gonna come back, and I'm gonna resume the meeting at 4:30. Okay, let's resume what we have. So I just hope that you if you have any questions, just quickly raise your hand or interrupt me, because this is a small class. It's quite flexible for us to do some adjustments and get some discussions during the lecture. For the review today, I want to go through them as quickly as possible, and then we can go back to the actual topic of this class. So we have one last topic left, which is about the probability and statistics, and this one is especially useful for us to work on the discrete choice model, which is for the multi choice in the transform planning. I will not go through those details. There will be a lot of details in these slides. I will not go through so many details in the class today, and hopefully you can read through them by yourself after class. So the first thing is about the definitions of the just a moment. Just a moment, let me readjust the presentation mode. Pretty weird. That's pretty weird. Just a moment. Hopefully it's working this time. Okay, let me see whether it's working or not. Still not working. Just a moment. Let me. I'm gonna exit the sharing and share it again. Okay. Okay, and it works. Okay. So for the probability theory, this is a widely applied for a lot of transforming studies, and also the for the data analysis we need the probability theory, the machine learning, the some big data analysis. They all rely on the probability and statistics. Here I will start from the very fundamental part about the definitions of the some key concepts in the probability theory. The first one is the random variable. The random variable could be categorized as the discrete random variable and the continuous random variable. For the discrete random variable, they represent the possibility that for one specific value that you can select from the set of the population. And if it's a discrete random variable, means that you will have the countable number of the values. Say that x1, x2, x3. It could be measured. You know how many possible values. And the probability of x will equals to the value of equal to the what's the chance for you to get the value from the set from the whole population. We usually use the letter p to represent the probability. P xi represent the probability for you to take the value of xi, and say that we have the value from 1 to infinite. If we do the summation about the probability of all the possible values, then the total probability will definitely be 1. So it means that you must select one value from the set of the from the data set or from the population. And here the little p is defined as the probability mass function PMF. It's only applied for the discrete choice model, discrete random variables. And we also have the cumulative distribution function, the CDF, which will represent as capital Fx. It will describe the probability that the random variable is less than certain value. And if we say that the for the capital Fx, it will represent all the values of the x less than the little x as we specified, and we need to summarize the probability of all those candidate values. The CDF is applied for the random discrete random variable. It can also be used for the continuous random variable. Here we have one typical example about the discrete random variable, assuming that we have the demand size of the random variable choosing from the values of 1, 2, 3, and 4. We have 4 possible values, and their probability is 1/6, 1/3, 1/3, and 1/6. If you sum them together, it's 1. And the probability mass function, and the with that we can find out the probability mass function. So for x equal to 1, the probability is 1/6. And for 2, it's 1/3. 3 is also 1/3. And 4, it's 1/6. Add them together, definitely will be 1. So that's the probability mass function. And for the CDF, the cumulative distribution function, it will represent what's the probability when the value is less than the x. So if for this case, for capital X is smaller than 1, you do not see any value about the x smaller than 1. So the probability is definitely 0. But for the x equal to 2, x less than 2, you will see that there's one value that is 1. So this is a 1/6. And this, for x smaller than 3, it includes the value of 1 and 2. So that is 1/6 plus 1/3. And for that one, x is smaller than 4, you have 1/6 plus 1/3 plus 1/3. And for the value, for all the other values, x higher than for x higher than 4, then that is a 1/6 plus 1/3 plus 1/3 plus 1/6, that is a 1. So for capital Fx, is actually f infinite. It should always be 1. It means that it covers all the possible values. So this is the discrete random variable. And then the next one, which is also more commonly applied one, is the continuous random variable. In this kind of variable, you will not have limited number of the values. Instead, you have the infinite number of the values. The values is continuous from the lower bound to the upper bound. And for the continuous random variable, there exists a non-negative function fx, and this would be the probability density function, that is the PDF. So we have to know that for fx, it's non-negative, so it's always equal to 0 or higher than 0. And if you have a value or a set of the value, x belongs to the set of B, say that x from x larger than x1 and smaller than x2, then the probability of x from x in this set of the B will be the integration of fx in that region. So for this specific example, if this is a B, then you're gonna have integration from x1 to x2 for fx dx. So which would be the area? Basically, that would be the area that will be the area covered under that region. This is the probability for you to choose the value between x1 and x2. And of course, if you do the integration from minus infinite to positive infinite, means that you will cover all the possible values, then the total value will be 1. So this is one of the important conditions for you to identify whether the probability function is valid or not. If you do the integration from minus infinity to infinity, it should always be 1. And of course, you need to make sure that the function is non-negative. So that's the definitions for the probability density function. And if we have the small intervals, say that from x to x plus delta x with the interval x is, you can then find out the probability in this interval, and we can then use this probability. We can use this probability to identify the cumulative distribution. The cumulative distribution definition of cumulative distribution for continuous variables will be the same to the random variable. It indicates what's the probability of the capital X smaller than certain value. For capital Fx, it will represent all the values, the probability of all the values less than small x. So that is integration from minus infinity to x. That is Fy dy. It could be if we have discretized them, it could be summarized for all the, it could be the summarization of all the small intervals, put them together, you get all the cumulative distribution functions from minus infinity to infinity. And the distribution will be similar, like start from minus infinity to eventually reach to 1 at the positive infinity. So this is the definitions about the PDF and the CDF for the continuous variable. And the next thing I'm going to show you here is the examples about the continuous random variable, and let's see how we can identify that this random variable is valid. This probability density function is also valid. Here we will consider on PDF. We are provided with the PDF of the random variable, and this is the it's actually an exponential random variable. Fx equals to 1 divided by beta times exponential of minus x over beta. And if you draw this PDF, you can see the value of Fx is decreasing over the time. And also remember here, you should remember that for the PDF, 1 divided by beta is not necessary to be less than 1. It could be, it can also possible to higher than 1, or could be a very large value. But we need to make sure that the integration of this one, the errors behind this one will be 1. And this is the actually the CDF, the cumulative distribution function of the previous distribution. So the fx actually comes from the definition. We do the integration from the minus infinite to the value of x, and with that you have this kind of blue line as the CDF, and you can eventually see that you're going to approach into the value of 1 for the to get the feature of the CDF. And for the random variable, we also want to get some properties. The mean and variance would be two important variables to measure the a random variable. First, for the mean, or say that as expectation of the random variable. Usually we use the mu or ex to represent the mean of the random variable. If it's a discrete random variable, we can use this equation, do the summation of xi times pxi for all the possible values. That will give you the mean value. If it's in a continuous random variable, we do the integration from -infinity to infinity of the x times fx. So that's how we're going to get the mean value. Also, we have some properties for the mean value. Usually, the mean only measures the central tendency of the random variable. If you have the see that if you have the a constant times the random variable, then the expectation of e times the expectation of c times x will be c times the expectation of x. So this one is always true. And if we have two random variables, x and y, the expectation of the summation for these two variables would be the summation of the two expectations. So that is ex and plus ey. This is regardless of the independence. So it's not necessary to be independent or not for the two variables x and y. The second variable to measure the property of the random variable is the variance. It shows the how concentrate the variables it is. Usually we use the notation sigma square or the variance x to represent the this variable, and sigma square is defined as the expectation of x minus mu square, which would be the deviation to the mean value of the random variable. It can also be written as the expectation of the x square minus mu square. This applies for the for all the for both discrete and continuous random variables. And here there will be two examples about the variance. These two distributions actually has the same mean values. Both of them will be mu, but for the figure on the left, the value of mu is large, and on the right is small. With that, you can see that for the distribution on the left is much flatter compared to the one on the right. With a smaller value of the variance means that the deviation from the random variable to the mean value is small and is more concentrated. So you have this kind of spike for the distribution, but for the one on the left with large variance, it will be flatter, much flatter. So that's the effect of the variance, and it's also the reason why we want to measure the variance. It can give you exact shape about the distribution. And regarding to the property of the variance, if you for the production with a constant c, the variance of the cx will equal to c squared times the variance of the x. And for two variables x and y, the variance of the x plus y at most time is not equal to variance x plus variance y, but this equation exists only when x and y is independent to each other. If it's not, then we cannot have this conclusion. And also sometimes we use the square root of the variance to measure the concentration of the distribution. And that's kind of the square root is called the standard deviation, or we sometimes just use the sigma to represent the standard deviation. And usually for the standard normal distribution, the probability of the variables in the range of mu minus sigma to mu plus sigma is around 0.68. So this is actually the common value for the standard normal distribution. Of course, you can extend the coverage to find out the different percentiles or different coverage of the distribution. Another variable another measurement for the random variable is the covariance, and the covariance shows the what's the relationship between two variables, how much of the variables can be explained by another variable. So the covariance is defined by this equation. It will represent the expectation of the variance of x, the deviation of x to its mean, times the deviation of the y to its mean. And you can also simplify this one as expectation of x times y minus ex times ey. So this will give you some simplification to calculate the covariance. Also, if the covariance can be applied to measure what's the dependence of two variables. Say that if y is also x, means that they are the same. Then the covariance of x and x will just be the variance of x. So it means that they are exactly the same. But for all the other values, if the covariance is equal to 0, means that x and y are totally independent to each other. If the value is positive, is higher than 0, means that it's positively correlated. Means that if x is larger, y is probably be larger. And if x and y, the covariance of x and y is negative, means that they are negatively correlated to each other. Means that x is larger, y will be smaller. So that's the definition of the covariance. Also, there will be some additional features about the variance and covariance. For example, for the variance of the difference between two variables, the variance of x minus y, it equals to variance of x plus the variance of y minus the 2 times the covariance of x and y. If x and y are independent to each other, then which means that the covariance will be 0. Then variance of x minus y is just the variance of x plus variance of y. If x and y and they are totally independent to if x and y are dependent to each other, where y equal to x, then definitely you will get 0 values. And the other thing that we want to define is the correlation. It's another measurement about the variance, but it will try to narrow down the range between -1 and 1. The correlation is defined by this equation. It shows the ratio between the covariance of x and y and the square root of the variance x times the variance y. So the value, usually the value of the covariance of x and y is between -1 and 1. If it's 0, means that x and y are not related to each other. If it's close to 1 or close to -1, means that x and y are highly related to each other. So it's a good way for us to quantify the relationship between two random variables. So with that, I introduced most of the concept about the probability theory. And the next thing I want to briefly introduce is the stochastic process, which will be related to the it's a kind of the collections of the multiple random variables. So it's basically the stochastic process will consist of multiple similar random variables, and they usually will follow the same distribution, and they might be comes from the same experiment. And if the collection is if we have the set of the collections x1, x2, x3, then without the continuous values, then we say that they are the discrete time stochastic process. But if there are some continuous values over time changing continuously, then we define them as the continuous time stochastic process. So those two are different based on the values that we can, the possible values we have. Here we can see one example. Considering that there's a single server queuing system, they have the independent arrival time and independent processing time. The arrival time is A1, A2, A3, A4. The processing time is P1, P2, P3, and P4. And with that, we have a set of the a set of the variables of AIs and the PIs. Then we can define a discrete time stochastic process about the delay in the queue. What's the actual time we need to wait for the request to be solved? So for the delay, for example, for the first request, the delay is definitely 0, no one's in the queue. But for the future request, the delay is determined by this equation. Is the maximum of di plus pi minus ai plus 1, depending on how long you process the previous request and what's the interval for the next request to arrive. And this definitely the delay should not be less than 0. So you have to have the maximum value, have the value higher than 0. And so that's the stochastic process. To deal with the stochastic process, usually we're going to need to estimate the mean and variance of the stochastic process. And here, assume that we have n random variables. It comes from the same distribution. Those we define them as independent, identically distributed IID random variable. So it means that they all have the same distribution. They are independent to each other. And then we can estimate the mean with this equation. So we just summarize all the values of xi and divide the number of the observations n. And for the variance, it's a little bit different. We do the summation about xi minus the mean value square minus n minus 1. So divided by n minus 1. So you need to, this n minus 1 is applied for you to find out an unbiased estimation of the variance. And we also can mathematically derive the variance of the unbiased estimator, which would be mean value and variance. For the variance of the mean value x bar, that will be the sigma square divided by n. Or in the for the data you observed, it could be modified as s squared divided by n. So this is the variance of the mean value from the stochastic process. But for the stochastic process, we have one thing that is not clear. It's about how much difference is the estimated value to the actual value, because we only have n samples getting from the distribution we defined. We don't know the actual means. We just have an estimation about the mean from the sample. So to estimate the precision, we need to precision about the about the estimation of the means, we need to have the confidence interval for the mean value. How confident we can say that the mean value is false in this region. So to define the confidence interval, we first assume that x1 to xn is an IID random variable with the same mean, and we don't know the value of mean. And we want to find out the 100 times 1 minus alpha percentile. So say that alpha, if alpha is 0.05, it will give us as 95 percentile. So this is the common percentile we applied. So with that, we can find out the confidence interval for the 100 times 1 minus alpha confidence as x bar plus minus t n minus 1 minus half alpha times the square root of the s square divided by n. And here t is in the t distribution, which is quite similar to the normal distribution, but it's not exactly the same. I will give you the upper and lower bound about the confidence interval with the confidence of 1 minus alpha divided by 2. And this figure actually shows making the comparison about the t distribution and normal distribution. You can see this difference. For the t distribution, it's related to the degree of the frequency, and usually for the with higher degree of the frequency, you're going to be close to the normal distribution. And if we for more information about the confidence interval, if we have a large number of the independent variables that we observed, say that if the n value is sufficiently large, then we can see that the t distribution will be similar to the normal distribution, or they will be close to normal distribution. In that sense, we probably don't need to use the t distribution. Instead, we just use the normal distribution based on the common mean and common standard deviation to find out the confidence interval. And the also the if x is not a normal distribution, say that if for some distribution that we collect, the number is not large enough, and the original distribution of x is not a normal distribution, then it's problematic. The distribution, the t distribution may not be close to the normal distribution, and you will find out in a larger deviation from the confidence interval you estimate to the actual one. So in that sense, in order for you to make it more accurate, what you need to do is like you need to dump this small n value. Instead, you try to make sure that n is large enough. And usually we want n to be larger than 30 to make sure that the distribution of the mean value follows a normal distribution. So that's one common threshold we need to apply to get the confidence interval. With that, I think I'm finished all the review parts about the matrix operation, the calculus, and also the probability theory. As I mentioned previously, it's quite a brief review. I just introduced those concepts, and you have to read through if you are not clear about some topics, you have to read through the materials I share with you, or you need to find out the course materials from your previous program. And I will also have another hour for this class. And do you have any questions before I jump to the next lecture? Any questions you have? Okay. Well, you can always type your questions in the meeting chat, or raise your hand later if you recall anything. I will keep this PowerPoint open, and later on we can go back to the to any questions. And the topic that I want to cover for the rest of the lecture today is the economic demand theory, which is one kind of the foundation for the travel demand analysis. So let me go through the. Let me quickly check whether it's opening or not. Okay. So for the first chapter of this class, we want to find out the traffic flow models and identify the relationship between the traffic flow models and the economic demand theory, and see how we can use in this theory to derive the to estimate the flow that we can assign from one origin to a destination, how we can use that one to identify the demand and supply, and so on. So the first thing I want to introduce, because we are working on the transporting area, we want to learn is the transporting supply and demand. So we know that the for the demand, it will represent the potential trips or the potentials for the traffic flow in the network. While the transportation is usually defined as the derived demand, which means that for the trip itself, it does not have any values. So people taking the trips because they want to go to their destination, they want to take the activity in the destination. They do not take the trip because they want to drive on the road. So we need to think about that the transportation is a derived demand as a consequence of the activity, and we also recognize that this kind of movement of the people of the good will generate the actual cost for the activity that they have to do, or for the products you want to sell. And the other things about the third things about the equilibrium assumptions. So usually for the trip that you have to take, you will have the two costs, two values. One is about the utility, which is the benefit or the utility that you can obtain at the destination, at the activity that you take at your destination. The other part is the cost that you have to spend for the trip. For the transporting supply and demand, we want to make sure that the value or the utility derived from the travel will be the same to the cost of the trip. So that will be the three important assumptions we have made before we start the transportation supply and demand analysis. So first, let's go to explore what's the potential. The first assumption was the potential for traffic flow in the network. I believe you are all quite familiar about this kind of fundamental diagram. This shows the relationship between the flow and density. This is one typical relationship, a triangular triangular fundamental diagram, when the road is not congested, you're going to observe a linear relationship between the flow and density, and the vehicles are moving at the constant speed when the density when the road is not congested. But when the road is congested, go to the side on the right. We define as the unstable flow. With more vehicles on the road, the flow will be smaller, and this reduced flow is caused by the reduced speed of the vehicles. And of course, you will observe the reduced speed at a higher density. So, we will start from this fundamental diagram. In this fundamental diagram, when the road is free, it's not congested, the demand is defined as the flow. It's just the flow, which means that how many, it's just exactly the same to the number of the vehicles traveling on the road. But the tricky part is on the right side, when the road is congested. The actual flow is shown as the red light, but in reality, the demand is much higher than red light. The reason for us to observe the for us to resolve this red line, this flow, this low flow, is because the road has some capacity constraints. So we will actually have a higher demand on the road, but the supply of the traffic network is smaller. In a general case, we assume that the for the traffic flow models, the demand at the congested case will be the capacity of the road. So this is the general case. Of course, there will be some specific theories which is sometimes they may have their own definitions about demand, but this would be the general case that we're going to use to define the demand. At the non-congested case, it's just the flow. At the congested case, it's a higher than flow, and in most cases, it's set as the capacity. And now let's have the more detailed analysis about the first assumption. The demand of the transportation is the potential for the traffic flow on the road. So we have some very simple implications. For example, let's just consider the transportation as a regular economic good, as the commercial goods that you purchased in the supermarket, like in some of the food, some of the grocery stuff, and so on. Just assume that they will be the same. We will, for this kind of product, for this kind of economic goods, we will usually have two functions. One is about the demand, the other one is about the supply. As the planner, we want to balance the demand and supply. But here, let's just assume that there are two functions, and usually the demand is determined by the supply. In the meanwhile, the supply is also related to the demand. So these two functions are highly related with each other. But for the transportation system, we will have some specific definitions about the demand and the supply. For the point one, usually we're going to use the volume of the traffic to represent the demand. So that's what we do in transportation system. How many vehicles can travel on the road, or how many vehicles they would like to travel on the road to represent the demand. So with that, we just say that the demand here is the volume on the road. We use the notation capital V to represent the demand. And that's the first point. And the second point, the transportation is the derived demand. and it does not generate any value by itself. So this means that the trip and activity cannot be viewed separately. If we consider the trip as an independent goods on the road, then probably no one going to take the trip because it won't generate any activity. Only when you combine the trip and activity together, you will find that the trip is meaningful. You take the trip because you want to take the activity at your destination. And usually we're going to use the a utility to represent the benefit you can gain from the trip. The utility of the trip can of your trip and activity will include the total utility of the trip and the utility of the activity at the end of the trip. So we define them as UT and UA. And of course, when you are considering the utility, you need to think about the cost you have to spend. For the cost of the trip, the whole things, the whole trip and the activity, it will be the cost of the trip, how much money you need to spend for the trip, the ticket fares, and also the probably if you drive by yourself, the time and the gas you spend, and also the cost of the activity. If you go to some theme park, you need to purchase the ticket. So it also consists of two components: the cost of the trip and the cost of the activity. And for the estimation of the demand, it will be determined by these two values: the cost of the utility, the total utility, and total of the cost. So with that, we can say that the volume, or we say that demand of the transporting system is a function of the utility and the function of the cost. But one thing we have to, based on our assumptions, like the transportation is the derived demand. The transportation itself does not have any utility. So usually we assume that UT is 0. With that, we have the demand is determined by the utility of the activity at the destination, the cost of the trip, and the cost of the activity. And usually for most of the situations, the utility of activity and the cost of activity will be some constant values. Only for this one, the PT, the cost of the trip, it's affected by the traffic conditions, which means that it's also affected by the volume. These two are affected each other. So this is actually the tricky part for us to deal with. And this is the conclusion we get from the second point. And to analyze the cost of the trip, we need to think about the fundamental diagram, as we mentioned previously. But we definitely want to simplify the analysis. Here we say that we can ignore the impact of the tolls, just assume that the cost of the trip is only related to it's only a function of the travel time. And then for any type of the road, the travel time usually the travel time is an inverse function of the speed. So this, if we are given with the distance, usually it's an inverse function of the speed. With a higher speed, your travel time is smaller. With a low speed, travel time is higher. So in order to identify the relationship between the travel time or the cost of the trip and the flow, we need to recall the we need to recall the fundamental diagram. And the fundamental diagram actually shows the relationship of the flow as the function of the speed and density. So here rho is density, s is the speed. And we can then go back to the fundamental diagram that we just showed. So for the fundamental diagram, when the road is not congested, the flow is increasing with the density. When the road is congested, the flow is decreasing with density. This is the common trend for the fundamental diagram. And now what we care about is the what's the relationship between the cost and the volume. So here, flow is the volume we know, and density is the number of the vehicles at a unit distance. And by extending this fundamental diagram, you can actually find out the speed density relationship and the speed flow relationship. So this would be the three figures for the fundamental diagram. And now let's see how we can find out the relationship between the cost and the speed and the volume of the road. So first of all, let's see that from the fundamental diagram we can find out the maximum capacity, the maximum flow, which would be the capacity of the road. That will represent what's the highest flow, what's the highest demand you can observe in the network. And now let's try to draw the relationship between PT and the volume. And also we know that PT is the inverse function of the speed. First of all, when the road is not congested, if the road is not congested, the speed is constant. For this example, it's always 70 miles per hour or 120 kilometers per hour. And we can then see that if the road is not congested, we will have the constant cost, because the speed is always the same. For 2 kilometers, they will always spend the same time to travel and arrive at the destination. But when the road is congested, the situation will be different. Say that for the volume of enter the congested region, for the volume of in this case it's probably 1800 vehicle per hour, then you will have the speed, which would be the slope of this red line, is actually reduced compared with the free flow speed, and that's the that will be around say around 30 miles per hour, and you can then find out by changing this value of the volume. You can then find out the speed. Find out the speed of the road on the road, and with the PT as the inverse function of the speed, you can then find out the value of PT. And basically, once the road is congested, by decreasing the volume, you will have the higher cost because the road is more congested. And when the road is not congested, the travel cost will be constant at all different volumes from 0 to the capacity. So this is the typical relationship between the travel cost, the cost of the trip, and the flow. We also have another example about the green shield fundamental diagram. The green shield fundamental diagram is not quite realistic to represent the real world traffic conditions. Instead, it assumes that the flow, the speed of the road is a linear function of the density. With a higher density, the speed will be smaller. And with that, they derive the concave relationship between the flow and the density. And also they can find out the relationship between the flow and the speed. With the similar process, you can then identify the relationship between the travel cost and the volume. So basically, the volume can only reach to the capacity. The demand can only reach to its capacity, that is capital Q. For the green shield fundamental diagram, the even under the non-congested case, the speed is not constant. The speed is actually decreasing with respect to the increased density. So the highest speed can be observed when the flow is 0. And then it will gradually decrease until it reaches to the capacity. So with that, you can find out the gradually increase of the cost of the trip with increasing flow at the non-congested region. At the congested region, the trend will be very similar. You're going to observe the flow will decrease with the increasing density, and of course the speed will be reduced. And with the reduced speed, you will observe the much higher cost of the trip. And that's the part you're going to observe for the reduced flow, and you have the increased demand, increased travel time. So that's the that's one example. Another example comes from the green shield fundamental diagram. And the third one, which is widely applied for the roads in North America and in both US and Canada. This is called the BPR function, Bureau of the Public Road Function. It shows the directly gives you the function about the trip cost with respect to the volume and the capacity of the road. It's actually in the stochastic model. And this one, if you go to check the expression of this model, you can find that by increasing the volume, the cost of the trip will be higher. And if you draw the figure, you can see that the red line is the BPR as described by the BPR function. But in reality, this part, the yellow region, is not achievable because it's impossible for us to get the road over congested. Instead, we need to find out some mechanisms to describe what happens when the road is congested. So the this model is quite good for the non-congested scenario, but it's not accurate for the congested part. So this is another example about the relationship between PT and the demand. Of course, you can see that in this equation, the cost is not only the function of the volume, it's also related to the capacity. So if the road has a higher capacity, definitely you can move your boundary to the larger values, and this indicates that you're gonna have a different relationship between the cost and the volume. So at least from all these examples, from all these examples, we know that PT is determined by the volume and also the capacity of the road. But in reality, there will be the situation will be more complicated. You know that in reality, for example, for the local road, we will not only have the straight road segment, we also have traffic signals. The traffic signal will affect the efficiency of the road. So what we have is like usually for the straight road segment, for each straight road segment, we have one relationship between the trip cost and the volume PT and the V. And for the intersection itself, due to the signal timing plane, you can also find out the relationship between the PT and the volume. And this actually applies for all the links on the road and all the intersections. So if we put them together for the entire road segment, you need to add the cost for the cost of the link, all the links, and all the intersections. And that will give you the overall relationship between the cost of the trip along this road and the volume. You will means that you probably will have the larger cost of the trip to move this amount of the volume on this road. On freeways, we will observe the similar trend. For the freeways, you can find out the relationship between the PT and V for each straight freeway segment. And on the other side, if the freeway has some on-ramp meters, which will also control the number of the vehicles can enter in the freeway during the unit time, then you will have the relationship between the cost and the volume, which is determined, which will represent the ramp metering delay. And for the whole freeway segment, if we put all these costs together, you will also have the similar trend. For the relationship between the cost and the trip. And this indicates that, with these two examples, it indicates that the cost of the trip is not only related to the capacity, to the volume, it also related to how the traffic on the road is managed. So we say that the management, the operator's management strategies, say that a capital M. So we will see that PT is a function of these three variables: capacity, volume, and the management strategies. So that's what we conclude from the from those examples. And then now we can then put all these three together. Like usually we can find out the relationship between the cost and the volume. And if we have three different capacities, you have three segments, we have three different capacities and management strategies. In one section, it has a signal timing plane 1, and then in the next section, you have signal timing plane 2 and capacity Q2. And the third one, you have signal timing plane 3 and capacity 3. With that, you're going to have three different relationships. And for the entire road segment, you need to add them together. Add them together, you're going to get the integrated flow and the trip cost relationship. Another thing that we want to mention here is like for the capacity of the road. Let's probably take the intersection as an example. The capacity of the road is also determined by the signal timing plane. So it's related to how you control the signals. So we should say that the capacity Q is a function of the management strategies. And another thing you need to consider is about the investment, how much money the government would spend or the city would spend to upgrade the road segment. Definitely with more money spent on the road, the capacity could be improved. So we have the Q as a function of the management strategy and also the investment. So by introducing this concept, we will then claim that PT as a function of management strategy, investment, and also the volume. So that's the additional information we can get from this analysis. And now we can then put all of them together and get a single line to represent the relationship between the trip cost and the volume. So for this line, this relationship is determined by the management strategy and also the investment. And so that would be the demand part. The next thing we want to consider is the supply part. What's the supply that the transport system can provide? So first, let's recall the cost. The cost is we say that is determined by the cost of the trip and the cost of the activity, which would be PT plus PA. And we want to use the equilibriums to find out the volume based on the utility that you can get activity and the cost you need to spend for the trip and activity. But in the previous analysis, we know that the cost of the trip is determined by the volume and also the management strategies and the investment. So for the total cost that we need to estimate for the trip, we also need to think about what's the value of PA. As the PA is the cost of the activity, usually it will be a constant value, the constant amount of the money you have to spend for the ticket, and also for the meal or for the other unexpected expense. So usually compared with the transportation system, the PA is not related to the flow on the roads. So it's only about the destination. It's not related to the flow on the road. So this is a constant. And if we put these two costs together, PT plus PA, put them together, then you just simply move the line upward a little bit. So we just simply move from the original value to the to some value above with the gap of PA, which would be the cost of the activity. So this is the total cost that you have to spend for the activity, including the transporting cost. And then for the demand side, we have the demand curve. Demand V is a function of the cost. With the definitely with low cost, the volume would be higher. But the But in order for us to determine the demand, we need to think of considering the activities, the utility of the activities. For example, let's consider the activity A, and if we know the distribution of the utility for the activity A, which means that we know the distribution of UA, and we also know that there is an amount of the how the population in that area will choose the activity depending on the utility, based on the utility values. And assuming that the probability is given, so we have the CDF, the cumulative distribution function for the utility, and with a higher utility, the probability will be larger. And now let's recall the equilibrium equation. We find that V is determined by the utility, and the total cost. And we also know there's a distribution about the utility. And now we need to go to check what's the probability of the utility that is less than the total cost. So which is just the if we go to check this one, which is just the FP, right? So this one shows the probability that the utility has the value less than the cost. And of course, once you are provided with this probability, you can then find out the probability that the utility is higher than the cost. That is 1 minus FP. So this is the one we have the higher utility. As the rational person who is making decision about the utility and the and also the trip, usually we will making a decision about whether the utility that we can get is higher than the cost. If the utility can get from the activity is less than the cost, then usually that means that you won't take the trip because you will spend more than what you can get. Only when, based on your judgment, the utility is higher than the cost, you're going to take the trip. So it means that for one rational person, the probability for you to take the trip is 1 minus FP. When you are provided with the cost of the trip is as capital P. So this one, with that, you can then find that the volume, the expected number of the volume is 1 minus FP times N. N here is the total number as the population number. It's population number. And the 1 minus FP will represent what's the probability of each person to take the trip. And it also represents what's the probability of the utility is higher than the cost. So this one, with this equation, we can then identify the volume that is will be applied from the origin to the destination based on the utility and the cost. And now starting from this conclusion, we will have some constraints. First of all, for the extreme case, say that if the cost is 0, if the cost approaches to 0, it not necessarily means that the volume will go to infinite. It's impossible. We always have some limitations about how many of the trips can be taken at the destination. So we have the limited number about the trip when the trip or the cost is reduced to, it's minimized to 0. This would be the extreme case. And also there's another limitation. We can see that when the cost reaches to certain value, say that, for example, if we want to go to the Toronto for or to go to Niagara Falls to enjoy some festivals, the cost of the trip, original cost of the trip is $20. Probably it's $20 you decide to go, but gradually it increased to $30. Maybe only you will reduce your intention to go to the Niagara Falls, and then if it further increase the price to like $100, maybe now all you or your friends would like to go to the drive to Niagara Falls. And in that sense means that the volume will be 0. So we will reach to another extreme case when the cost approaches to the value, the volume will be 0, or the capacity or the probability for the person to take the trip will be 0. So in that sense, we will find out the two ends. One is the ideal case, no cost of the trip, the maximum flow you can observe. The extreme case, cost is too high, no one gonna take the trip, and the flow is 0. So for that, with that, we will be able to find out the 2 points from the region of the cost and the volume at the volume equal to at the cost equal to 0. You will find out the maximum volume as V0. At the cost of P0, the volume is also 0. And there will be some lines in between connecting V0 and P0 in this region to show the relationship between the demand and the supply. And this kind of line, how the line is determined, is related to the amount of the cost you have to spend at the activity, the cost you need to spend on the road, and also the PT is determined by the is also related to the capacity, or it's a function of the management strategies and also the investment. And the shape of this line is affected by a lot of factors, but we as in this class we need to find out a way to find out the characters of the shape. With that, we're gonna introduce the a term which is called the elasticity, and the elasticity epsilon represents the percentage change in the volume divided by the percentage change in the price. So to use some notations we defined, that will be delta V divided by V divided by delta P divided by P, which would be the changes of the volume over the changes of the price. And for the if we can identify the continuous function about the relationship between P and V, then the elasticity would be dV over V divided by dP over P, and you can further simplify this one as dV over dP, which would be the inverse of the first order derivative for P with respect to V times P divided by V. So this is the definition about elasticity. I guess I don't have enough time to cover the rest of the lecture today. I will just keep this one for the next lecture and continue the introduction about the definitions of elasticity. And I will stop at the page 15, and you can have some you can go through the slides by yourself after the class, and maybe next lecture you will have better understanding about the nodes, and we're gonna have the fluent discussion about this topic. Okay, with that I think it's almost the end of the lecture today. So before I leave the meeting, do you have any questions, any concern?
Hi, Dr. Yang. Could you please give us some example about the utilities?
Okay, if there's any questions, Jing, I saw your hand is on.
Hi, Dr. Yang.
Jing, do you have any questions?
Yeah. Can you hear me?
I cannot hear you.
We can hear. We can hear you. Jing is speaking.
Okay. Okay. How about now? Can you try it again? I just can hear Xiaoyan, so Jing were able to.
Hello. Can you hear me?
Yes. Yes.
Dr. Yang, could you please give us some example about utilities?
Yeah, we will have some examples later. This is about the theoretical explanation about the utility, and we're gonna have the examples about the utility functions and some typical utility functions and the utility functions in transpose system. So don't worry about that. We're gonna have all the examples later.
Okay.
Yeah.
Actually, I have a question about the stochastic process at the page 52. So could you please go back to the last slide about the stochastic process?
52.
Yeah. It's the last function. Could you explain it more?
Yeah. So you know that the x bar, if you go to check the first one, x bar is is a mean of n random variables. So x bar
it's a sample mean, and it could be a unbiased estimation of the population mean, right?
Yes.
Yeah.
It's a x bar is also a random variable.
Yeah, I know that.
So for the random variable, you can have the
variance.
Variance. The variance is but if you go to check the do the derivation about this variance, the variance of this one, you can get the first equation. Well, if we really want, you probably can check the reading materials I shared with you. There will be some detailed descriptions about how to get this equation.
I know how to get the second last equation.
Yes.
But I don't know how to get the last one.
So for the last one, it's just simply replace the variance. If we want to make the shorter explanation, just simply replace the sigma square with the s square, because s square is an unbiased estimation of the sigma square. If we are only provided with the samples x1 to xn, you don't know the value of sigma square, or you don't know the value of mu. You only know the estimated value s square. So we need to replace sigma square with s square.
So the last one just means the mean of the variance of the sample mean.
Yes.
So the last one just the mean of the second last one.
Yes. Yeah.
All right. Thank you.
Also, I see the questions. Just a moment. So for the office hour, yes, I have the office hour at 11, and also I have the office hour today. So there's a meeting link there. If you want to join the office hour, just join the meeting. join the meeting, enter the office hour channel. Let me just quickly show you the so we have the office hour channel here, and if you want to join the office hour, just enter this meeting and I will join immediately after that. So with that, it will be you can bring any questions you have. Yeah. Every Tuesday from 11 to 12. Okay, any other questions? Okay, if no, then that will probably be all today. And I will upload the video and share with you on Avenue and YouTube so you can watch them again. Okay, great. Thank you very much for your time. And I will see you next week.
Thank you.
Yeah, thank you.
Thank you.
Bye.